I get asked all the time, Amelia, what's the next big thing? What trends are you seeing making waves in the world of electronic engineering? And my follow up answer is most often another question. Well, how long do you have? Because this might take a while. But one overlooked trend driving big change in our industry can be found in only three characters, two numbers and a letter to be exact. Yep, I'm talking about 48V. 48 volts. Today, there is a huge trend toward 48-volt power delivery. The power efficiency and subsequent reduction of power loss makes a transition to 48-volt power delivery systems an absolute must to keep a competitive advantage in a lot of different industries. But how best can we transition from our legacy 12-volt systems to a 48-volt PDN? How can we efficiently convert high voltage to 48 volts? And what about a strategy for 48 volts to point of load? What do we do then? Well, my friends, you've come to the right place because we're talking all about this and more. Hi, I'm Amelia Dalton, host of Chalk Talk. In this episode of Chalk Talk, Tom Curatolo from Vicor and I explore the what, where, and how of 48-volt power delivery networks. We also investigate the components of a 48-volt ecosystem, the advantages of a high-density modular power design solution, and the 6 things you need to consider when transitioning to 48-volt power systems. And before we get started, don't forget to click that link. There you can find even more information about this topic from Vicor. Hi, Tom. Thank you so much for joining me.
Thank you very much for the opportunity to speak about Vicor, our products, and the 48-volt power delivery networks. This is a very exciting time for Vicor, and we really appreciate the opportunity to inform people about this. Thank you.
Absolutely. Okay, so we're talking about how we can accelerate the transition to 48-volt power systems today. So first, Tom, walk me through what all will we be covering today?
So what we'd like to talk about is the problem statement, of course, and help people understand what you're up against to begin with, but then move into the evolution of the 48-volt power delivery network. And then from there, we'll take it to the advantages of the power module design, and we'll compare that to both a silver box, which is more of a centralized solution, and a discrete solution, which is also very popular, and what the pros and cons of those are. In addition, we want to focus on a 48-volt portfolio, and we refer to it as an ecosystem, so that we're converting high voltage to 48 efficiently, and also 48 to point of load. In addition, bridging between 48 and the legacy 12-volt buses and peripherals. And then we'll close with maybe 6 things you need to consider before transitioning to a 48-volt PDN.
Fantastic. Okay, so Tom, what do you think is driving the trend toward 48-volt systems?
Well, first and foremost, power levels in many different market segments are going up. Many of our customers really want to gain a competitive advantage. And so this is what's driving a lot of the industry trends these days. We refer to power delivery networks as the architecture of a power system. And that is focused on maybe improving the power delivery and the efficiency. So one of the best ways to do that is to move up in voltage. So oftentimes 12 volts has been the legacy, as I mentioned in the previous slide, but the move to 48 volts now has taken hold in many industries like automatic test equipment, unmanned aerial vehicles, robotics, automotive, and also AI and data center racks. And the key here is to reducing the power loss, the I squared R losses. So going to a higher voltage makes a big difference.
Absolutely. So there's also a trend driving 48-volt power delivery in industrial systems as well, right?
Oh, that's so true. The world now is transitioning to 48-volt power delivery networks to take advantage of reduced power losses, primarily for greater efficiency. Telecommunications was the first market to recognize these benefits. And then high performance computing followed shortly after, with the open compute, which was supported by both Google and Microsoft. And then from there, it was further enabled by Vicor's own architecture, factorized power architecture. More recently, electric vehicles have decided to move in that direction where 48-volt benefits are even more significant. And comparing it to 12-volt PDNs, the 48-volt PDNs make it possible to use lighter, more flexible cabling, and it saves cost and complexity. And we'll cover that. But today, more and more power designers for industrial systems are moving to 48 volts. And their challenge is that 12-volt PDMs have been around for decades, and there's a wealth of knowledge and an installed technology base for 12-volt PDMs. That's what you're up against. So Vicor now has the technology and the product portfolio to ease the transition from this 12-volt change to 48 volts.
Okay, so Tom, earlier you mentioned a silver box power supply and how they compare with power module designs and discrete components. So, talk to me about this silver box power supply approach.
Right. So in the past, typical power solutions have been addressed with a power supply, which is often referred to as a silver box or a shoebox type of power supply. And it's basically components enclosed in an aluminum chassis with input and output connectors. And this approach may be considered for its ease of use, but there are limitations that should be considered based on the requirements of the application that go beyond just the volts, amps, and watts. So often, the power requirements are addressed later in the design process, making it hard to define the final power requirements in regards to electrical and mechanical and thermal management. And often the process of specifying and receiving a custom silver box brings with it a longer lead time than other approaches. Also note that the silver box is typically easy to implement, but that doesn't provide the advantage that modularity does to change or expand quickly.
So, I would imagine that there would also be limitations when it comes to the discrete component approach as well.
That's true. And in comparing it to the discrete approach, which is used to configure a power solution, offers the system engineer the capability of a precise design because it is discrete for addressing the specific characteristics of each load. But here, the trade off is better suited to a situation where there is plenty of time to address any challenges with the complexity and the limited flexibility that would hamper meeting aggressive timelines. Plus, potential changes to the design would have a significant effect on your time to completion. The discrete solution is typically considered a hard approach in regards to a longer design and integration effort. Plus, there's risks due to supply chain issues, and while changes are possible, it will take additional time to repeat the work and revalidate the design.
So, Tom, how does a modular power delivery help solve these issues?
Well, in regards to the advantages of the power delivery network, considerations in regards to efficiency, which relates directly to less losses in heat dissipation, plus weight, small size, and scalable power are the significant attributes to the success of this type of power design. The modular approach can provide a shortcut in design effort and minimize the bill of material, providing lower risk in the supply chain. It is worth noting that manufacturing these high power density modules on a panel is a low cost, scalable process that is similar to semiconductors on a wafer. And this is what goes on inside the Vicor factory in producing these type of modular solutions. A key advantage of the high density power approach, like in the UAV realm, in the unmanned aerial vehicle realm, is that the less real estate and lower weight a power solution takes up, the more space available for the payload, which really is important to these type of designers. Let's go over two real-world examples based on the work Vicor has done with leading innovative UAV manufacturers. The focus is on two specific applications, but the information here is useful across all UAV power systems.
All right. So before we go much further, Tom, walk me through the general 48-volt ecosystem. What kinds of solutions are we talking about?
Okay, this is a very good question because what we want to view the 48 volt as more of a hub, if you will. So, in many systems, there's a lot of different ways that people are implementing voltages. And this diagram shows you specifically that going from high voltage to 48 is a very common approach. Higher voltages certainly greatly minimize power losses. And you can think about a tethered UAV with a long cable, how high voltage may be a big advantage in that regard. But bringing it down to 48 volts so that it can address point of load converters is key. So we broke it into three sections: high voltage to 48, 48 to point of load, and then also addressing the fact that where there are 12-volt legacy power delivery networks already, it's easy to convert up to 48, or if you need to go down to 12, going from 48 to 12. So this outlines our product portfolio and basically the Vicor ecosystem, if you will.
Okay, so Tom, what about converting high voltage systems to 48 volt? Are there some design concerns or approaches we should consider?
Yes, absolutely. As I mentioned, there's a number of ways that this is done in different market segments. And certainly getting down to 48 volts, whether it be generated from a rectified single or three-phase AC source, is very common, or even more in the automotive world and certainly in the robotics and UAV world. Coming from a high voltage battery is often where the source is. So, what we're talking about is converting hundreds of volts to 48 volts with minimal loss. And there's two primary ways of converting. And one is the fixed ratio DC to DC converter. And these are ideal for larger applications that require minimal power loss in the conversion process. One of the reasons is that they are very high efficiency. We're talking upwards of 97, 98% efficiency, and very small size, very high power density with a lot of power in a very small package. In addition, there's also regulated DC to DC converters, and these are ideal for applications that require precise bus voltage regulation.
So, Tom, do you have any examples of real life applications that you can share?
Yes, so in the next slide, I'd like to talk about a case study where we're talking about tethered unmanned aerial vehicles or UAVs. And what we do when we do these case studies is we try to understand what the customer's challenges were. In this case, they wanted to optimize the power delivery through the tether, which would probably be obvious. They also wanted a rugged, highly integrated power supply for high reliability and certainly efficiently convert high voltage to safe 48 volts. Now, where Vicor comes in is we can significantly reduce the tether size, weight, and drag with our products. We can easily take this high voltage down to a 48 volt and make the 48 volt a hub within the UAV itself. And again, we're focused on putting a lot of power into a small package. So this comes into a lightweight, highly efficient conversion for the high voltage tether to the SELV or safety extra low voltage bus that's on board the UAV. So these modular designs, they support flexible design requirements so that we can be easily changed if loads change or anything like that. So this is a very powerful way to implement a power delivery network. So continuing on in the case study for tethered UAVs, this slide shows the PDN, both the ground station and onboard the UAV itself, with the tether being an 800 volt solution to get to the onboard. So in this regard, the BCM isolates and steps down the rectified output from a single phase, or in this case, three-phase AC to 48 volts. And a second BCM, the 6123, steps the 48 to 800 for the transmission across the tether. And then on board, the third 6135 is used to step down the 800 to 48 volt on board the vehicle. So the BCM provides 3.5 kilowatts of power for either a step up or step down conversion. And we're talking 97% plus efficiency. So size and weight on the ground station and the UAV are significantly reduced with this type of approach, and as are the diameter and the weight of the tether, which is really critical. Certainly, in this type of an application, the tether, the smaller size and the lighter gauge that's used is a big advantage. And here you can see the type of loads that it has to support on board is propulsion, camera, a sensor, and some logic, which are easily addressed with the buck regulators. But those key BCMs really make the difference in this type of an application.
Okay, so what kind of solutions does Vicor offer to convert from high voltage to 48-volt power?
So, what we're talking about is the challenge that is powering high current, low voltage loads from a 48-volt bus. And basically, we've got a number of products upstream of that, which we refer to as high voltage to 48-volt power modules, one being the BCM 6135. Bus converter module. So BCM is obviously an acronym for bus converter module. It's an isolated fixed ratio converter. It is also capable of bidirectional power flow. And in this case, the input is 520 to 920 volts. And because it's a fixed ratio, it just divides the voltage down. So in this case, it would be dividing by K of 1/16 to get between 32.5 to 57.5. And it is capable of delivering up to 80 amps. And here's one of the big key things is the peak efficiency is 97%. And you can see the size of the package, 61.3 by 35.4 millimeters. That's the outline, and the height is 7.3 millimeters. Then on the other side, we talk about the isolated regulated solution. And here you have a what we refer to as a DCM 9223. And again, you might note that those numbers are actually the footprint dimensions, 9223. And the DCM stands for a DC to DC converter module. And this again takes an input of 160 to 420, which matches up nicely with power factor corrected AC front ends that we talked about earlier, and then produces a regulated 48 volts. And that could be trimmed between 36 and 52 if you need to. But the power level is capable of 2,500 watts. And again, peak efficiency, we're talking 96%, which is very impressive in the industry.
Absolutely. Okay, so what about 48-volt to point of load, like you mentioned earlier? What kind of challenges and approaches are we talking about here?
So this is a very good challenge and a competitive challenge as well, I might add. So powering high current, low voltage loads from 48 volts typically requires a buck regulator. It's space constraint, points of load need to be, a factorized power solution. So we've gone and rethought the concept of taking a bus module and then doing a non-isolated point of load kind of approach. We've taken it to what we call factorized power architecture, where we're actually doing current multiplication at the point of load. So that's a proprietary approach. And we do the regulation upstream from this current multiplication. So it really is a new way of thinking, a new way of implementing a power delivery network. There can be a multi-phase regulation, as I mentioned, and then voltage division is also occurring at the point of load. So this is a new way of thinking about how to implement a power delivery network for very challenging type loads, like high performance computing is a really good application to consider here.
All right, so what about an application in this case?
So, some of the applications that we've been very successful in that we want to show is another case study on instrumentation. So, the customer in this case certainly had space constraints that were limiting their performance, and they wanted to maintain signal integrity without introducing EMI noise, both radiated and conducted. They wanted to manage the heat, which improves reliability, so avoid equipment failure, if you will. So in that case, Vicor came up with these high density converters that provide more power within the same space than what they were using. And one of the reasons we were able to do that is because of a topology and technology that we refer to as sine amplitude conversion, or SAC. And this is a very low noise topology. And because it's so low noise, because it's taking advantage of a sinusoidal waveform internal, it allows the use of less filtering, hence saving space in regards to the typical EMI filter that would be required. And also the benefits are high efficiency and the advanced chip, which stands for converter housed in package. And that's the new type of packaging that Vicor now manufactures in our new factory. This capability reduces heat and the need for extensive cooling hardware because we're getting to much higher efficiencies. And the way the product is designed, it's very symmetrical in how it dissipates heat. So, therefore, it's taking full advantage of all the surface area of the package. So, for the next slide, the power delivery network in more detail, this is off of an AC source, which was converted to 48 volts. And the 48 volts is then converted down to the specific load voltages. So, the test fixture required 36 volts, and programmable devices needed a 6 volt and then a 12 volt for the peripheral interface. So the sine amplitude converter comes into play with the VTM that's shown there for the 6 volts and the NBM, which is the non isolated version, for 12 volts. And these are very high efficient products. The packaging combines itself with planar magnetics and a very low profile, so it greatly improves the thermal management of the device. And where there's needed very high efficiency, meaning low power dissipation. This is a key thing. And keep in mind, the DCM that's shown for the test fixture, this is a family of products. So you can choose many different output voltages. But again, the efficiency on this product is, high 90s, 2.5 kilowatts. So, and these products can also be, all three of them can be easily paralleled for much higher power. So it's a very interesting portfolio of products that makes providing solutions very easy for the end user.
So, what kind of solutions does Vicor offer here?
So, what we're talking about for 48-volt to point of load power modules is four categories. One is the DCM, which I was just speaking about, and this has got three package sizes: a 4623, a 3623, and a 2322. Again, those are the footprint dimensions in millimeters. And you can see the outputs are a variety, anywhere from 3.3 up to 48 volts. And there's also a number of inputs that are offered, starting from 24 volts all the way up to 400 volts. And so these input ranges are typically focused around specific market segments and those requirements. So it makes it very easy to implement these products. And I mentioned earlier that they are easily paralleled with a very passive approach for paralleling. Further on is the ZVS buck regulators, and I'm going to talk about both these at the same time, the ZVS buck boost regulators. These are both non-isolated, but again, there's a variety of input voltage ranges and output voltages and current capabilities up to 22 amps, and most notable is the peak efficiency at 98% and 97% for the buck boost. So these products are very small. The only addition that they need is an external inductor. That, with a fuse and small caps around it, product is easily implemented into many different solutions and can be used as a what we call a non-isolated point of load regulator. And then in the final column is where how we implement factorized power that I was just talking about in the last case study. This is a PRM and a VTM. It's basically a chipset, if you will, where you have a pre-regulator module, the PRM, and a voltage transformation module, the VTM. We refer to the VTM as a current multiplier because that's basically what it is. It's a fixed ratio converter, and it has a K factor, which is like a turns ratio on a transformer, and therefore it's dividing voltage down but multiplying the current. So that really enables applications where you need very low voltage at high current. This has been a very innovative solution for many of these types of applications. Certainly, the parts can be used as standalone, but together as a chipset, it becomes a full, complete DC to DC converter capability with regulation, isolation, and transformation. So we really like to focus on the capability of that current multiplication because that's a big deal in regards to how it can perform for very challenging load types with dynamic changes in loads. And also, one thing I haven't mentioned is the capacitance multiplication too, where you can put capacitance upstream at a much lower value and still get the same amount of energy storage. And we'll cover that later. But that's also an interesting thing that's enabled by factorized power architecture.
So, Tom, you mentioned legacy 12-volt systems as well. So, talk to me more about that.
Yeah, so bridging 48 and legacy 12-volt buses has been something that's been brought to our attention on a number of occasions. And what I mean by that is many systems have embraced 12 volts, what I refer to as legacy systems. You're probably well aware of that in the automotive world with the 12-volt battery, the lead acid 12-volt battery. Everything has to run off of 12 volts in a car. So that's where 12 volts has become a very tried and true way of implementing power and many different other market segments as well. But the advancement, when there's more power that's needed in these systems, getting up to a higher voltage can really become a very competitive advantage. So, bridging the gap between 12 and 48. If I already have 12-volt source, but I want to move to 48, can I easily do that? And Vicor has thought about some innovative products that easily allow that. And basically, it's a fixed ratio DC to DC converter that's ideally suited for this bridging capability. And it's referred to as the NDM 2317. So, this non isolated bus module, the beauty of it is it's bidirectional. It's a 48 to 12, but it can be a 12 to 48, meaning its powertrain can be used in either direction. You can put 12 volts in on one side and it'll come out 48 or 48 in the other. Again, it's fixed ratio, so there is a K of 1/4. So it's either multiplying by 4 or dividing by 4. And that's a very easy way to bridge the gap. And then for downstream subsystems that require precise bus regulation, it can be used with these buck boost regulators or even the DCMs as well, depending on what the application requires and what the load requirements are.
All right. So, can you share any specific case studies for these kinds of solutions?
Let's look at the burn in thermal chambers. That's an application that we've been involved with for many years, even with our older products. So, what are the challenges here? Specifically, increasing the demand for burn in thermal chambers. So, customers are up with all the semiconductor and things going on, builds going on. They need more thermal chambers, they need to build them. There's an increased demand. So, time to market and getting these things done quickly is very important. The factory floor space is limited, so scalability of these systems is important. Maybe we put in a small system, but we want to scale it to a larger system. So that kind of a design decision needs to be made. And then the growing IC device under test performance and the complexity. So that means the loading on some of these IC devices needs to be taken into consideration and addressed with the right power performance type of package. So in the Vicor solution, we're typically going from 48 to 12 in a compact, thermally efficient package for these applications. And that works really well for this type of environment. Power density of the Vicor solution enables the higher burn-in throughput within existing space limitations. So that really allows space savings to really take place with this power density. And fast development and reduced overall test and burn-in costs comes down to the fact that implementing a modular solution is relatively straightforward, and there's a lot of information on the Vicor website to help a designer easily implement it, as well as Vicor FAEs that are very skilled in helping customers. So all this together really makes for a great solution in this type of an application. The next slide also shows the power delivery network in more detail. So here you can see the low voltage Vicor BCMs and advanced chip packages. They perform a fixed ratio conversion with high power density and high current density. This has integrated planar magnetics in the BCM that minimizes the height profile. So that saves a lot on a card rack or whatever when you have minimal space to put chips within a card rack. And then the MBM series is very efficient. We're talking high 90s efficiency, close to 98%. A major improvement in regards to thermal management, and it's been adopted for many ATE type of applications. So I think this PDN is very characteristic of a lot of the burn-in chambers today where you have to address analog, NAND, SATA, SSD, 12-volt buses, and device under test. Further case studies, if we can look at one more, the precision inspection equipment. Customer challenges were to ensure high quality and high inspection yields. They needed a higher demand for defect detection, and they also wanted to increase power needs, which results in larger noise filters within the system. So they wanted a solution that could address all those three aspects. So with Vicor, we could drive transition from the outdated 12-volt bus to a more efficient 48-volt bus. We can look to that by using our sine amplitude converter, which mitigates noise and reduces filtering, which was a big deal in this application. Again, high efficiency and advanced packaging reduce the heat and allows uniform and predictable dissipation. Big advantage. And moving to the next slide, we can see the power delivery network, which was the first critical step in moving from a 12-volt to a 48-volt. So you can see there, this shows a 48-volt battery. The BCM takes it easily down to 12 volts. And you also have part of the PDN powered off the 48 volts. So this way, it's sort of a hybrid between a 12-volt bus and a 48-volt bus, and it keeps the compact size and low profile of the Vicor modules, simplifying thermal management, and in turn, simplifies the mechanical design for these types of inspection systems.
All right. So, Tom, what specific Vicor solutions would you suggest here?
So, and keep it in mind with our new packaging, the innovative packaging that we have these days that take into account surface mount capability as well as through hole. You can see in this slide the DCM is shown. In this case, there's a 48 to 12 DCM that's shown here in a non-isolated regulated package. The input is 40 to 60, which is very common in the high performance computing. The open compute that I had mentioned earlier in the document specifies 40 to 60 volt in. And it regulates at 12 volts, but it can be easily trimmed down to 10 volts or up to 12.5. And power is that there's two package sizes here, but the highest power is up to 2 kilowatts. And the efficiency is very impressive now, which is 96.5 for a regulated converter, is very impressive. The small size of the package, 36 by 17 with a 5.2 millimeter height, is so impressive. The NBM, which I mentioned before, is the bridge oftentimes used for 48 to 12 and has bidirectional capability, has the input of 36 to 60. That output depends on the input, right? Because it's a fixed ratio converter, so it's a K of 1/4. So you're dividing that voltage down. The power level on these products is 2,400 watts max. Efficiency is up to 98%. You can see there's two package sizes, surface mount as well as a through hole package as well.
All right. So, overall, Tom, what do you think my audience should keep in mind when it comes to transitioning to 48-volt systems?
Yes, so we thought about this and we wanted to bring the right things to bear here. So we broke it down to 6 things to consider when transitioning to 48 volts. We're talking 4x efficiency gains in regards to power density here. So it efficiently converts power by a factor of 4 times. So this is really a major gain when it comes to transitioning to 48 volts. What you got at 12 volts, 48 volts is roughly 4 times the advantage in regards to power. So that's one of the main reasons for considering the transition to 48 volts. The next one down here, the safety myth. So one of the reasons 12 volts is very popular is because it's a very safe voltage. But 48 still falls into the safe voltage. And actually, it goes as high as 60 volts. But 48 volts is sort of the midpoint. And you could see a lot of our inputs are around 48 volts, 40 to 60, because, you know, depending on the source, it's never going to be exactly 48 volts in the real world. So the safety myth is people thinking that 12 volt, it has to be 12 volts for it to be a safe voltage. No, 48 volts is also considered SELV. And that's why it's been adopted in many industries, as I mentioned. The next one down, advanced converter topologies deliver value. So what we're saying in this regard is we've moved to new ways of manufacturing an advanced converter now, and we're able to provide a very cost-effective approach with these new topologies so that it's very competitive. And the value of using an advanced converter now makes a lot of sense. And with the higher efficiencies, which minimize heat dissipation and not so much concern on thermal management and how that plays, and reliability and as well as cost, those are big wins in that regard. In the next column, reliability and thermal performance. Well, that's where I was just going. Yeah, improving that is a big deal. And you're going to get there by certainly operating at lower temperatures. So you want a higher efficient device. And with high efficiencies in the high 90s, you're able to take full advantage of dissipating less heat into a system. This is a big win, but reliability calculations prove this out. The next one down, 48-volt ecosystem is expanding rapidly. So I was showing a slide earlier where the ecosystem can be from very high voltages, 800 volts down to 48 volts, and then 48 volts down to the point of load voltages. This kind of thing is becoming more and more popular, and you need all the right products to support it. So that's one of the things that you really need to consider when transitioning to a 48-volt system. And I just want to add as a side note that Vicor has been thinking along these lines too. And we have a lot of products that support each one of those activities, whether it being converting from 12 to 48, going from that legacy 12 volts, or that ultra high voltage down to 48 and using the 48 as a hub and then taking it down to the point of load voltages with either, non-isolated point of load converters or the factorized power architecture approach with PRMs and VTMs. And last but not least, hybrid strategies ease the transition. And what I was showing in the last case study is where intermediate bus conversion can coincide with factorized power architecture. So in power delivery networks, using different ones in IBC to a NIPOL or using our PM to VTM can be done in the same power delivery network. So that's what we refer to as hybrid strategies. And this makes an ease of implementing and winning solution for a competitive approach with your power system. So I hope this helps, and I think these are good points to consider moving forward.
All right. So, Tom, can you recap your main points for me?
Oh, please, yes, thank you. So in summary, moving to 48 volts delivers competitive advantage. And we're seeing that over and over again in many different market segments, in many different specific applications that we were mentioning earlier, whether it be in the UAV market or the robotics market or the ATE, which we consider the industrial marketplace, as well as the automotive world and high-performance computing. There is major advantages that give you a competitive advantage. And certainly all these systems are always increasing in power, and therefore moving to higher voltage like 48 volts makes a lot of sense. Now, high-density power modular solutions definitely provide a distinct advantage over discrete and silver box solutions. And we want to really summarize that a modular approach is an easy way to implement a power delivery network, but it also allows an easy way to scale the power delivery network if you have different size systems or you want to make changes. This modular approach is a major advantage where products oftentimes are the same size with the same pin out, so making a change is very minimal if the PC board is already laid out. So those kind of things are very important, and they give you an advantage over the discrete and the silver box solutions. And certainly time to market is an important point as well here in that regard that we covered earlier. And last but not least, the effective approach requires analysis of all three stages of conversion. And that's what I was saying, that Vicor wants to say that, look, whether you need high voltage to 48 or you need 48 to point of load, a lot of these have been considered, and it's really a building block approach. And last but not least, if you're still using 12 and you need to bridge to 48 volt, I mean, you really can't beat the NBM for being close to 98% efficient. And the ability of it to be bidirectional too is very key. And in summary, I think this really captures the overall capability of where 48 volts and transitioning really plays a major role in many markets going forward.
Fantastic. Well, I think that's all I have time for today. Thank you so much for joining me, Tom.
Thank you. Much appreciated.
And before we go, you didn't forget to click that link, did you? There you can find even more information about this topic from Vicor. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal. You can't miss it, it's right across the top. Or head on over to YouTube, youtube.com/EE Journal.